Come on.
Flip geometry!
Hey students in the break room making your video. We've done some triangle congruence proofs and we are going to continue in that trend. So your object here is to give the given statements on the following triangles. Okay, so here we have triangles ABC and triangles DEF, and our two-proof statement is we want to prove that they're congruent triangles. So take a moment and try and give me the given statements. So you're going to basically, normally you'd have a triangle and I'd have given statements and I'd draw on the triangle. Now I've drawn on the triangles, you're going to try and do the opposite. So I've drawn on the triangles, you're going to try and give me the given statements. So take a moment and try. Okay, so here I've put my given statements there. You can tell, I'm sorry about the shaky camera. You can tell that angle D is congruent to angle A because they both have two arcs there denoting equal angle measure or congruent angles. And angle C is congruent to angle F. Same reason, one arc, that means they are congruent. And line segment DF, remember DF with a bar on top of it means line segment is congruent to line segment AC, and I see that they're both denoted with this drawing here. So if I have these given statements and I want to get to this two-proof statement, what might I use? And go ahead and write it to proof. Okay, this is really just a one-step proof. This is our 0 step, and this is our step 1. So I've got my conclusions. I've essentially just written the given statements, and I've justified that by saying they're all given to us. And then I can write my to prove statement. Triangle ABC is congruent to triangle EDC right here. And here's where I'll commonly see the biggest mistakes on tests or quizzes or homeworks is students will just say, oh, there's two congruent triangles, and you'll make up a theorem. You'll say something like the triangle congruence theorem, or something very generic. You'll say, I don't know. There's all sorts of crazy stuff. You'll say they're both isosceles triangles. We can't even know that, right? So they might be. These are very generalized triangles with no angle measures or lengths written or described, so they're just schematics right now. So they might be isosceles triangles, but they don't have to be. So we have to think about what do we have and where can we go with it? Well, what do I have given the triangle congruence theorems that I know? Can I say that it's an SSS, a side-side-side triangle congruence theorem? Well, they look the same, but I don't have it marked. If I had this marked with 2 dashes and this with 3 and this with 2 and this with 3, then I could say that, but I don't have that marked. So I have to go with what I am told, very explicitly, what I am told, and where can I go with it? Can it be an SAA? Well, I do have two angles and a side, but I have to think about which side is included. So the included piece of a triangle, remember triangles are comprised of 6 different pieces. I've got 3 angles and 3 sides. So if I had 6 pieces, I could say S, A, S, A, S, A. So this goes from side to angle to side to angle to side to angle. So I have to do these things in order, right? So I have to walk around my circle and tell them in order. So what do I have in order? I've got an angle, a side, and an angle. And that tells me if that is true with the other triangle as well, then I'm going to use the angle, side, angle, triangle congruence theorem. And that's what we'll justify with. The angle, side, angle, triangle congruence theorem. Okay, your challenge and what you'll bring in first thing in the morning, this is like effectively your homework, is to look at this drawing. I've got a triangle ABC and a triangle EDC, and you're going to write the given statements and then complete a 2-column proof. And here it is. So shouldn't be too much of a challenge. You are going to use a theorem we've learned in the past. And it's going to be regarding these angles. And then you're going to use one of our new triangle congruence theorems. So that is your challenge. Leave that up. Have a great day. Hey students, we're here again. We're gonna do a little bonus lesson here. So we've got an Indian, and he's got a teepee, and you can see his teepee, if viewed in profile, is a triangle. And then we have a mountain, and that mountain, viewed in profile, is a triangle. And if the Indian puts his teepee on top of the mountain, you can see that they are overlapping figures. The triangle overlaps with the mountain. It doesn't always have to totally overlap. So I've got another picture right here. You'll see triangle ACD overlaps with triangle ABE, and we could write it like that. When I wrote triangle here, it's somewhat redundant. You don't have to really say triangle. Would be read triangle, triangle, ACD. It's kind of like saying ATM machine, automatic teller machine. Is like saying automatic teller machine, because that's what it stands for. That's what's happening. So we can use the fact that figures overlap in lots of proofs. If I have a hexagon, A, B, C, D, E, F, and I draw two chords between FB, two line segments FB and AC, I have two overlapping triangles. It can help to draw them. I've got triangle ABF, and I've got triangle ABC, and I put little hash marks for us. We know regular polygons, every single angle measure is the same, and every single line segment that makes up the regular polygon is a congruent segment. So they're the same length. And notice they overlap. So let's see if we can use these figures to complete a proof. Okay, so let's keep in mind this hexagon ABCD EF. Hexagon six-sided, it's a regular six-sided figure. It's equiangular and equilateral. So what are our givens? Well, we know it's a regular hexagon, so we're going to say A, B, C, D, E, F. A, B, C, D, E, F is a regular hexagon. Oh, I'm not even close. I'm going to use the rubber bait. Okay, so this is our given. We've got a regular hexagon, and we justify it by saying it's a given statement. Keep in mind, this is the hexagon we're talking about, A, B, C, D, E, F. Okay, the next thing we're going to prove, our goal is to prove that the line segment BF is congruent with the line segment AC. Let's look at what that is. Line segment BF, that's this segment right here, is congruent to line segment AC. It looks like it is. And as we said, most of the proofs we do in geometry is self-evident. So they're fairly obvious, but we have to make a logical sequence of steps that leads us to this irrefutable conclusion. So we're going to prove, we've said that it is a regular hexagon. The next thing we might say is that line segment AF is congruent to line segment BC. So AF is congruent to BC. And how do we prove that? That is because both of these exist on the perimeter of my regular polygon. So we can say this is the definition of a regular polygon. And our third step, so keep in mind this whole chapter is about triangle congruence proofs. So that gives you a little bit of a clue of which kind of direction we're going to take this. We're going to try and prove that these two triangles are congruent. And you can see I'm going to try and prove that this is a side angle side triangle congruency. I only have 3 pieces of data, but that's enough for me to realize that these are totally congruent triangles. The next thing, they share a side. The next thing we need to prove is that these triangles share a side. AB and AB are both part of these triangles, so let's go that direction. AB is congruent to AB. This seems like we don't need to say it because it's so obvious, but in fact we do in order to use our next point. So in order to say this, we've gotten a little bit used to this. This is the reflexive property of congruence. This means it's congruent to itself. congruence. Okay, so we can mark this one. And we could even use one hashtag, or not hashtag, who am I? Hash, because it is for sure the same length as the other segments because it's on the exterior of our regular polygon. So we're getting there. What else might we choose? Well, we've used this property of the regular polygon being equilateral so far. That means that every side is the same length. Let's see if we can use a property that every angle is the same, that regular polygons are equiangular with our next proof in this argument. So we're going to say angle FAB is congruent to which angle? See if you can look at it. Which angle FAB and which is congruent? Well, any of these, but the one I want to know about is ABC. Angle ABC. Angle FAB is congruent to angle ABC. And again, we're going to use another fact. We're going to say that this is a definition of regular polygon. Okay, so we've proven this side, this side, this side, and this side are all congruent. We've proven that this angle and this side, this angle are congruent. So we can use one particular triangle congruence theorem. So we're going to prove that these triangles are the same. So we're going to say triangle FAB is congruent to triangle ABC. And this is our SAS, side angle side triangle congruency theorem. Okay, are we done yet? Normally we've been stopping there, right? So we're not done yet. We have to prove that line segment BF is congruent to line segment AC. So we're gonna, that's our last step. BF is congruent to line segment AC. And you all might even see this coming. Well, I've got two congruent figures, and these are corresponding parts. Boom, boom. They're in the same locations relative to my other defined parts. So we use the corresponding parts of congruent figures theorem, CPCF. That is the end of our proof. Okay, so that is one way that we can use overlapping triangles to prove things that otherwise might struggle to prove. Main ideas can have overlapping triangles. They don't all have to share the same space. They can, but they don't have to. And then I can use them with triangle congruence theorems to prove all sorts of things. Have a good night.